Regular squarish slab supported by beams can be easily analyzed, and designed using moment coefficient method. British, Eurocode and others codes allows the use of this simplified method. Design moments are derived from table of coefficients, based on slab edge conditions, or continuity, and ratio of Lx, shorter dimension divided by Ly, longer dimension. In ProtaStructure, slabs can be designed using slab strip function. Ensure analytical strip is chosen in the slab properties. Ensure slab edge continuity or type are set correctly. Ensure slab strip start and end condition is set correctly. Click and drag the slab strip across slabs to be designed. Do this both horizontally and vertically, orthogonal direction. Slab reinforcement will be designed and shown on the plan view. Use slab analysis and design function to generate the report. There are other methods to design slab. Kindly refer to the Prota Help Center.
Before design of any slabs, it is important to review the settings. Go to Building Setout, Settings Center, Slab. We will go through the important settings. You can refer to Prota Help Center for more detail. Design. Support top bar. Support top bar's extension lengths are determined using the factors specified in top steel extension lengths fields. Parameter. Concrete cover. If you leave this field as 0, then the concrete cover will be determined based on active codes. Slab design combinations. There is option to use all combinations or use only vertical combination. Slab span lengths and analysis. Clear span means distance to the edges of the supporting beams. Centerline means distance between centerline of beams. Column node interpretation only applies if finite element slab design method is used. It is not applicable to analytical strip. Wood armor effects refers to the torsional stiffness of the slab using the finite element method. It is not applicable to analytical strip.
Ribbed slab results collection method if for ribbed slab design only.
Rebars. The choice for rebar pattern is bent-up pattern and straight bar pattern. Minimum steel bar size, bar spacing and length steps can be changed. Steel bar edge clearance is the clearance of the last slab rebar from the beam edge. Curtailment options affects the detailing of rebar. They are largely self-explanatory. Appearance. View. These are additional options to display dimension lengths of the rebars. You can choose to print alternative label of rebars, example, use BB instead of B1. Slab hole. In this field, user can choose the visualization of slab hole in the model, either drawn as X or L. Click Cancel. Go to Plan View of Story 4 of the model. To recap, select any slab, right-click Slab Properties. When slabs are created, we did not specifically set the type of slab, but left it at 1. Type 1 means all edges are continuous, Type 2 means one long edge is discontinuous, with the rest of the edge continuous. If we want to design the slab using the coefficient method, the correct slab type must be chosen. This slab should be Type 3. Click Update. Close. Instead of setting the type 1 by 1, fortunately, there is an automatic batch function. Right-click on Slab folder in the structure tree, set slab types automatically. Set the minimum continuity ratio, above which that slab edge will be considered as continuous. Default minimum continuity ratio is 70%. However, it is entirely a user decision. Click OK. The slab type will be automatically determined as shown in the dialog. Note that slabs that are not regular and four-sided cannot be determined, as it is technically beyond the scope of moment coefficient method. It is up to the user to set the type manually or to design these slab using other methods, such as finite element method. Cantilever slabs, defined as type equals 12, is unique and need not be further classified. Click OK. These are the 3 slabs type that cannot be determined automatically. Let's assume you have set it correctly and decided to proceed with moment coefficient method. Go to Modeling tab. Click on the slab strip. The slab strip properties will be displayed. Set the direction to X for horizontal. The slab strip number start with 1, so the first strip label is X1. Slab strip type analytical strip is used for design based on the coefficient method. FE strip will be based on finite element analysis, which requires the floor slabs to be meshed. Choose analytical. When drawing the strips, it is essential that the correct at start and at end boundary conditions are specified correctly. There are three options. Slab. The strip starts or ends inside a slab. The bottom steel for the slab in question is not designed, but the span of the slab can be defined, and this value is used in determining the support steel. BOB, bending of bar. The strip starts or ends beyond an edge beam or wall. The support steel at the edge is bent down into the beam or wall. Cantilever. The strip starts or ends beyond a cantilever slab. For the first slab strip, we are going to cut from left to right as shown by the arrow. The start and end are both beams, hence correct boundary condition is bending of bars for both. Slab width will only be activated if slab boundary condition is chosen.
Scope width is only applicable for finite element strip, that is, slabs are meshed either using building analysis or FE floor analysis. It does not apply to analytical strip.
We will now cut the slab strip as shown by the arrow. Position your cursor between axis A and B, but to the left of axis 1, so that it is outside of the beam. Left-click to confirm the start of the strip. Hold down on Control key to lock to exactly horizontal. Then click the end of strip to the right of axis 4. Slab reinforcement will be designed and shown automatically on the plan view. The program will design all the bottom bars, B1, and the top support bars, T1. Draw another similar slab strip X2 to obtain the design for the slabs between axis B to C and 1 to 4. Zoom to this slab, where the strip does not cut through. For this slab, we can cut a strip through this slab only, as the adjacent slab is already designed. The start condition is still BOB. However, the end condition must be set to slab, as the slab strip ends at the adjacent right slab. The adjacent slab is 5 meters, hence enter 5,000 millimeters in the slab width at end. This is to ensure the curtailment of the top bar is correct. Now cut the slab strip across this slab only. The rebars will be designed. Zoom out. Next, we want to design the slabs between axis C to D. Since the left side and right side are both cantilever slabs, change the start and end boundary condition to cantilever. Draw the strip. A message of deflection failure for the cantilever slab will appear. Deflection is not automatically designed, it is checked. The user has to decide the next course of action, example, to increase the thickness or to use FE analysis for this slab. As mentioned earlier, technically irregular, non-squarish slabs are beyond the scope of analytical strip. Click OK to close the message. Now draw the vertical strips to design Y direction rebar for the slabs. Change the direction to Y. Reset the number to 1 again so that the strip label is Y1. Keep type as analytical strip. We are going to cut the strip from bottom to top starting from grid 1 to 2. Set at start condition as BOB. Set at end condition as cantilever. Cut this strip. Again, the prompt of deflection check of cantilever slab appears. Click OK. Continue to cut the next Y strip between grid 2 and 3. The start and end condition are the same. Cut the strip, ensure it passes the cantilever slab. Create the last Y strip between grid 3 and 4. All slabs are now designed. Close the slab strip dialog box. Go to Design tab, click Slab Analysis and Design. The Slab Analysis and Design dialog will appear with a summary of pass and fail status, utilization ratio and the reinforcement. Interactive Design. Select a slab strip. Click Interactive Design will redesign this slab strip and allow access to detail strip design. The table shows the summary of the slab properties and design results, including the rebar. If desired, you can click on the rebar to change it and then click on another cell to update.
Click Design. The standard 3 design options appear, which allows you to update the design if there are changes in the model. Click Close.
Click Report to generate the design report for this slab strip. Review the report. Close it. You can copy and paste rebars from one slab to the other using the copy and paste bars functions. Click Cancel to exit.
Double-click on slab strip X4, which has failed status. As you can see, the reinforcement passes but the deflection fails. Deflection can be improved by increasing the governing steel, in this case it's the top steel since it's a cantilever slab. Decrease the rebar spacing and this may improve the deflection check. Click OK when satisfied. Perform similar steps for any other strips that fails. If increasing governing steel does not work, then the slab thickness must be increased. Click Slab Strip Design, Batch Mode. The standard 3 option to batch check or redesign are available. Choose the first option to perform a batch check on existing steel without any modification. Click Design. Close. This will reconfirms whether the existing steel is sufficient overall.
Settings and parameter. Opens up the slab design settings in the settings center. Cancel. Filter. Allows filter by story, slab thickness and design status. Cancel. Copy bars and paste bars. Allow copy and paste bars of similar slabs marked with equal symbol. Only slab strips with the exact slab configurations can be copied and pasted. Click Design Report. The entire slab reinforcement design report of all slab strip is generated. Any failure in the design will be highlighted in the notifications pane at the left. Review the report and then close it. We have completed the slab analysis and design. Close the dialog box.